So I found this little short and sweet thing for us to talk about today. Beyond what is possible, new JWST observations unearth mysterious ancient galaxy. I've talked about this topic at length at this point, how JWST is kind of completely reframing our entire understanding of galaxies in the ancient past and galaxy formation in general. It's basically making us question everything we thought we knew about cosmology, everything we thought we knew about extragalactic astronomy, and the formation of these ancient structures that should not be there. This whole beyond what's possible thing, it is true. This is theoretically, based on everything we understand, like I talked about yesterday, just far beyond what should be physically possible for galaxies located at that position. The actual paper has a title that's a little more reasonable, but an extraordinarily massive galaxy that is formed its stars at Z greater than or equal to, or greater than or about equal to, 11. This is a very, very high redshift. They actually call it out, I think, in here. Yep, here we go. So 11.5 billion years ago, again, reminder, age of the universe, 13.8 billion years. That's a cosmic redshift, or a redshift of about 3.2. 1.5 billion years before that is a redshift of 11. So we're talking, 11.5 plus 1.5 is about 13 billion years ago. So about 800 gigayears, or 800 million years. 800 megayears, not gigayears. 800 million years after the Big Bang. So this is really, really like pressed up right against the edge of really what we can hope to observe with JWST. So this is kind of like the earliest thing, one of the earliest things we've ever discovered, that we've ever pointed a telescope at. So this is ancient. And also note that we went from 3.2 redshift to 11 redshift over the course of just 1.5 billion years, even though the 3.2 was at 11.5. This is not a linear scale. This is very much not linear. This is really, really neat stuff. We're looking really, really, really far back, and it should be noted that this galaxy is being observed, like it said in the article, at a much closer redshift, a much lower redshift than we expected stars to be formed at, and, well, let me explain why that's the case. So here is our good old friend, the spectrum. A lot of what we do in astronomy, a very, very good portion of it, is done using spectrographic data. These spectrographs can tell us a whole lot of stuff. Like, for example, you'll notice that they've actually gone ahead and marked with these dotted lines some very important features that we would expect to see in galactic spectra, which are different than solar spectra, but they are related because your stellar population that makes up your galaxy basically dictates what your galactic spectrograph will look like. This red line here, the one that's kind of looks like it's underneath everything else, this is the actual galaxy that we're talking about. The other one, this green one here, is a different galaxy that was also observed by JWST that has been shifted to match the redshift of this one. So effectively, we have this spectrum, which is what we observed this galaxy that's in the image here, the one that we're talking about to be, and then this green one is a different galaxy we understand a little better, that we have a lot more observations of, and its redshift has been shifted so it can just be in line with this other one. So we took the features that lined up like H alpha over here, we lined it up with where we saw H alpha in the current galaxy spectrum. We went and we saw the 4,000 angstrom break, and we lined that up. We saw the Balmer break, we lined that up. That's basically what we did to get these two aligned. They lined these two up so that we can compare them. Now, this one, this green one, is a galaxy we know a lot about, and it's one that we also know is pretty young. We know that this galaxy 20115 is younger in terms of its stellar population, so it's forming. It's still in the middle of stellar formation, starbursting. It is making new stars. It's making very hot, very blue stars that won't be around for really that much longer before they eventually burn out. But eventually you end up losing a lot of your blue population, and you start just having these old red stars that have been burning for a very long time. That's, like I mentioned a while ago, a red and dead galaxy. All of the stars that are left over in an older galaxy are redder, so we would expect a lot more in the red side of the spectrum than in the blue side of the spectrum. We kind of get a shifting of what that curve looks like. So over here, higher wavelengths in the red, we would expect to see greater number over here, so in that case a greater flux in that part of the spectrum, and then less over here if we're talking about older galaxies. The green one, the one that we understand pretty well, is pretty indicative of a very young galaxy. Not very young, but a young galaxy that's producing all of those A-type stars that we talked about last time, which creates this Balmer break. The Balmer break, again, being that point where any of those electrons that are in the second shell of hydrogen will get knocked out and ionized, so everything that is of that wavelength or higher will get preferentially absorbed by the interstellar medium. It'll knock away those electrons, they'll absorb the energy, and all of that will be lost on this part of the spectrum, on this blue end. Now, this Balmer break is really, really obvious. You can see it right here. It's this like little step down on this section of the plot. But if we look at the red, that's again the curve that we're kind of really looking at here. If we look at the red, that break doesn't really seem to have much of an effect. This is a very, very shallow fall off compared to this really steep fall off that we would expect to see from a young galaxy, which indicates, one of the things that indicates to us that this galaxy that we're seeing, again, very far away, especially compared to this other one that, we're referencing at the moment, this green curve, it definitely looks like this is a lot older than this green one, which doesn't make any sense. It's further away, so we should expect it to be younger, we should expect it to be having higher star formation, but this spectrum, and a lot of the things about it, like another thing, these like H lines, the H alpha, the H beta, and the H delta, those are all just not, I think this is probably H gamma. Yeah, I guess they just used a G instead of gamma for some reason. But notice in the green spectrum, huge dip, huge dip, huge dip. There's not really one over here at H alpha, but that's also just because it's really hard to resolve at that distance and that redshift. But then look at the green one. If we go to the more pronounced ones, this one's kind of got something going on here. H gamma's got nothing, and H delta's got nothing. So where these really big dips should be in a young population of stars, it just doesn't exist here. Another clue that this galaxy is a lot older than other galaxies that we have observed in similar regions of space. So all of that being said, this galaxy is shaping up to be quite a bit older than it should be. And not only is that a problem with the fact that it's so far away on its own, if it's that old and that far away on its own, that means it must have been around for even longer. So not only is it a problem to find a galaxy that is this progressed in its evolution at that point, it's even worse because if we trace it back, it's just so out of left field compared to what we would have expected from our current understanding of galaxy formation. And that's what this plot down here is really looking at. So this plot here is taking the object that we have in black, and it is comparing what the spectrum should look like for galaxies of certain ages. So this is a 500 million year old galaxy, a 0.8 billion year old galaxy, a 1 billion year old galaxy. And we can see sort of these effects that I was talking about before. If we look at the youngest galaxies, then you'll notice over here on the blue part of the spectrum, I can't show this part at the same time, but this is increasing wavelength. So we're going from blue on the left to red on the right. Over here we get in all of this blue area, this young galaxy is just really, really high flux compared to everything else, all of these other older galaxies. And if we look in the red, we get the opposite effect. This really young galaxy doesn't have a lot in the red because it's forming very, very massive stars that produce very blue light. As we get older, so we're going from blue to yellow or orange to green to red, it starts to shift, and we start to get more flux in the red region, less flux in the blue region. If we do this and we kind of plot this versus what we see, which is again the black line, we can start to see that some of these line up pretty damn well. The one that they call out for fitting the best, I think, is the 1.7 giga-year one. Let me check. Yep, this one, which is the purple one. So if we look at the purple one, it follows the black curve, which again is our galaxy, pretty substantially. It even follows it through this weird, it's not a weird dip, but through this magnesium dip. It follows it all the way through the 4,000 angstrom break, and then it tapers off a little bit at the Balmer break, but not much. It's basically a perfect fit. So this tells us that the galaxy that we're looking at, this really already too big to be true galaxy, that it's just got too much stuff in it, also was formed about 1.7 billion years prior to our current observation. That's just wild. Not like that doesn't happen. This type of galaxy shouldn't exist as it stands, and now we're saying that it existed in a form that was not possible even at the location we found it 1.7 billion years prior to it, right after the Big Bang. So something's very different here than what we understand, and I already showed this plot. Well, it's not this plot, but I showed a similar plot. This should look very familiar. This will give you deja vu from yesterday if you were around. That really drives this home. So what this plot is showing us is it's showing us the star formation rate at certain times that must have occurred for this galaxy to exist. The red curve and the green curve are two different models that are basically saying, hey, how much star formation rate do we need to match up with the data that we saw from this new galaxy? And you'll notice that they all peak, or I guess I should say they both peak. The solid red line is what we're looking at, not the envelope. The envelope is just statistical. It peaks all the way out here past the 1.75 gigayear mark. Same with the other one, which, this one's obviously much more of a step function, but it has the same thing where all of its stellar formation is supposedly happening really, really long ago. And in fact, it doesn't even start to pick up at all, even in the statistical modeling, earlier than 1.5 billion years. Compare that to these blue curves, which are what we should expect halos to look like based on what we know about galaxy formation. And this object was starting to form stars so much earlier than it should have been allowed to, simply based on the fact that something this big shouldn't exist. It shouldn't be possible for something this large to exist that long ago, given what we know, given what we've seen to get these curves, these dark matter halos that we have observed, or at least that we have projected, I should say. Now, mind you, all of this is rather speculative. We don't really know for sure what's going on here. Like, obviously, we have a pretty good idea. We know that this galaxy is a certain age, or at least it can be modeled as a certain age. We know that we saw it. We have spectrographic data for it. So it's not like we don't know what it is. The question is, how did it form, and is there something that needs to be changed? A cosmological shift could cause issues with other data we already have, so maybe it's not that. All of this is showing us that these galaxies that we are looking at, these big red dots, as we've called them in the past, or maybe we didn't call them big, they're tiny red dots or something. I don't remember exactly what the terminology being used was, but these really red, really old galaxies that shouldn't exist, but they definitely do. So this is really, really cool stuff. It's kind of heating up. All of the data coming in through JWST. When was this paper published, actually? So this was back in August of 2023. But it's heating up. Like, all of this stuff is coming out still, and we're not finding anything that's saying, hey, we were wrong. It would have been top page news. So it's real cool stuff. That we are finding things that very, very strongly disagree with what we would expect to see, given what we know. Because there's a lot more physics that we don't know, which is always cool. Other than that, though,